Hello and welcome to my video, lesson 4.4 on lenses. So here's where we're going to really dive into a couple of calculations, but also weird sort of unintuitive questions and answers in Physics 30 with light. So focal point of a lens is the point where all the rays would meet. Focal length is the distance from the center of axis of the lens, i.e. the center of the lens, to the focal point itself. Lenses and mirrors are different, so keep that in mind when we're talking about mirrors in the next video. Convex lenses have converging rays, and often, but not always, real images upside down. Concave lenses are diverging lenses and produce smaller, upright, virtual images with a negative focal length. And so with mirrors, just by the way, before you get there, mirrors flip this to convex. And then everything else holds true as well. Convex mirrors are diverging, versus over here, mirrors are concave mirrors, and those ones are diverging. So this is very, very important to keep in mind. Mirrors and lenses flip, but this one is interesting. This is always true. Convex lenses, on the other hand, can kind of change a little bit what they do. The magnification and height of the image can be used with this formula here. So it's basically the ratio between the image and the inverted image. Normally speaking, personally, I consider magnification as an always positive thing, i.e. you put in these absolute brackets, but considering there's a negative here, and oftentimes we put negatives within, it's not entirely clear. So if you put a negative for your magnification, I think that's probably more correct sometimes, but that's not something that I will focus on as much. So if I write that differently in class or on this video, that may be something to just keep in mind. Normally I just consider magnification as always a positive number. If magnification is, I'll say this, if it is bigger than 1, that means the object is getting bigger. If it is less than 1, closer to 0, it means the object is getting, or the image is getting bigger if it's greater than 1, and the image is getting smaller if it's less than 1. Okay, looking here, we have the formula that solves from the focal length to the distance to the object and the distance to the image. This is the formula we're going to be focusing a lot on in the next couple examples. Now, we can use that formula to solve a given question, or we can also solve it with a ray diagram. So we're going to do that first, the ray diagram version, and we're going to start with this example, or this step. So from the tip of the arrow directly to the lens, we're going to draw a line. Now, this is not always nice and easy to draw, but there you go. It's, like I said, not always easy to draw, but it's going this way towards the lens. Okay, once it gets to the center of axis, then it goes directly to the focal point. I'm just trying to make sure that I nail this as good as I can. There it is. Okay, so that's my first arrow. My second arrow I'm going to do in green, drawing a ray straight from the top of the arrow through the center of the lens undeflected. So it has to be, for sure, going through the center of the lens. So undeflected, so I've got it going all the way down here. Okay, because I've drawn it like this, now we can see where the lines meet. Actually, I probably should have written that here. Where the lines meet is where we're going to have the tip of our virtual image, or not virtual image, the tip of our image, I should say, which is showing up somewhere around here, based off of my drawing. And again, your drawing will probably be better on a piece of paper than it would be on the computer, but there it is. Now, considering that it is showing up over there, it is showing up inverted. It is showing up larger than the original, and it's showing up as a real image, because those rays that we see there are real rays. They're not dotted lines. We'll talk about dotted lines in the next one, but for now, that's a real image. So we can now measure from the lens, from the center of the axis of the lens to that image, and we can get a result that is probably pretty good. So we're getting around 16, so maybe I'm going to say 15.9 centimeters. And then the height, 5, maybe a little bit less than 5, so 4.8 centimeters. This is what I've measured on the graph paper. Now it says solve algebraically. So we can solve this algebraically to verify these numbers. We're going to do that right now. We're just going to use this formula, 1 over f equals 1 over dO plus 1 over di. We're going to rearrange this and solve for di. So first of all, 1 over di equals 1 over f minus 1 over dO. Now we're going to flip, i.e. put everything over, like 1 over everything. So this is going to be di, because 1 over, here, I'll just write this, 1 over di is what we're getting on the left side. But when you're dividing by a fraction, which is what we're doing here, it's like flipping and multiplying. But you can see that that's just di, right? So this is di on the left, and then on the right side it is not as nice. We can't just do that because it's 1 over the entire thing. So actually this one is going to be that whole thing written out. Okay, now we can go ahead and plug in our values of f and dO, which we can measure from the graph paper. 6 centimeters for the focal length, 9 centimeters for the dO. So if we were to write this into our calculator, it would be 1 over f, which is 6, minus 1 over dO, which is 9, and we get 18 as our answer. Well, it looks like our result is not quite perfect. I clearly didn't draw this super well, because our results are not ideally, like, they're not super close. I was getting 16 roughly with my counting, and yet 18 over here. So there's 2 centimeters off. It's not great, but it's not bad either. So that's fine. What we are going to now check, though, is also our HI and see how close that is. Our HO is 3 centimeters tall. So what we're going to do now is use the magnification formula. So HI over HO equals DI over DO, negative technically. So then you can solve for HI, which is HI equals negative DI times HO over DO. And this will get you negative DI, which is 18, times HO, which is 3, over DO, which is 9, and we get a result of negative 6 centimeters. And again, we got about 5, so again, this is not the most perfect of all drawings, but it's not too bad either. Okay, so with all that said, you can go ahead and pause the video now and try the same process with example number 2. I recommend that you pause the video at this point and you brighten your screen, put a piece of paper on top of the screen, and then you can try to trace this out a little bit, and hopefully from there you can get a good drawing. Or you can take a screenshot and draw on the screenshot with your phone or with your tablet. or you can take a screenshot and print it out, and then best is just to do this on paper. So pause the video now and try it yourself. Okay, so first step is to do the same thing as what we did in red, which is to get a line going straight to the center of axis of your lens, and then from there you're going to go straight to the focal point. The light rays are going to diverge in that direction, which means we're going to have this dotted line going in this direction down. So the light is being diverged, which means it goes this way, and the dotted line is not a real set of light, but it is helping us to perceive where that light would be. Okay, now what we can do is draw a straight line through the center of the axis. Again, trying to be as precise as possible. And it would go through undeflected. That's just what happens when you go through the center of axis. But on the back end, it does, you could draw the arrows continuing this way, but we know that that's not actually where it's going. So once you have this nice drawing created, now we can go ahead and see where they meet, which is right over here. And we have a smaller arrow showing up there. And notice that it's showing up with the dotted line of the red, which means that it is a virtual image because it's using a dotted line to get the result, which is where you think that it would be if you were looking with your eyes, but you wouldn't be able to project this on a screen. If it's a virtual image, you can see it with your eyes, but you can't project it, and it's because light travels off of an object and bounces towards our eyes. And so when we see the light bouncing towards our eyes, we assume it's coming from an object, but the object is not actually there. We've diverged the light into different directions. So it's not actually bouncing off an object. It's pretending like it's bouncing off that object. So anyways, it's a virtual upright image, and in this case, it's smaller than the original. And so one of the things you can do to kind of see if it's going to be smaller or bigger is if the image is if the image is closer to the lens than the original, then it will be smaller. If the object is closer to the lens than the image, then the image will be larger. So with all that said, we're getting a result of around, and it's not perfect, but it's somewhere around 1.8 centimeters tall, and DI being 4 centimeters, almost exactly. So now we can use the algebra to try to solve for the different values here. So if we just do 1 over F equals 1 over dO plus 1 over dI, we can do the exact same as in the previous question. And so we're just going to kind of skip ahead a little bit there. But 1 over F minus 1 over dO. But the trick with this one is you have to remember, because it's a diverging lens, the focal length is negative. Actually, we should write that down. Focal length is negative 6 centimeters. The distance to the object is 11 centimeters. And the height of the object, which we'll use later, is 5 centimeters. And that's just counting the number of squares. So let's go ahead and plug this in. So it's 1 over, and actually this is going to be the negative 1 because it's the focal length, which is a negative value. You could have put the negative at the bottom, it doesn't really matter. Minus, and then 1 over dO, which is 11. And so we get a result of, and I'm just going to convert this to a decimal, we get a result of negative 3.88. So we're going to just say negative 3.9 centimeters for our DI. Okay, this one's closer. Look at that. That's a lot closer. Now let's go ahead and solve for our HI. So just a reminder about how we did that before, but it comes from this formula about magnification. Okay, and then we just solve it for HI, which gives us negative DI times HO over DO. Which is going to be negative DI, which we already know is a negative 3.9, times HO, which is 5, over DO, which is 11, and we get a result of 1.77. Ooh, not too bad. 1.77, which we round to 1.8. And look at that. That's what we have here. So not bad at all. Yeah. So technically speaking, the DI in this example should actually be a negative, which we didn't recognize. And so you might need to just double check that with your with the algebra. It's not entirely clear. It depends on which side of the lens that it's showing up, but that's hard for me to remember because there's no good reason for it. So go ahead and double check that with the algebra. Okay, here is one final question for this video. Please press pause and see if you can do it yourself. Alright, so there are a couple interesting things with this setup. This is a lens that is convex. Okay, so this is convex, and this is concave. If that was enough to now try the question, go ahead and do that. But basically, we're going to have light rays coming in from the moon, coming in like this, and because it's convex, it's a converging lens. So the light is going to come across like this, and then finally it's going to come out straight here. The concave lens is going to straighten out that light beam, so it's coming out straight again. But you'll see that the light beam has now flipped compared to the original. So an interesting question. And also just keep in mind this magnification idea. You can stack magnification just by putting multiple lenses together. So 5 times multiplication and a 10 times multiplication will give you 50 times multiplication. Or magnification, sorry. Multiplication. Alright, I hope this video helped you better understand lenses and yeah, how to draw these ray diagrams and do some of the calculations around them. Hope the video helped, and good luck.